Hello, everyone, and welcome. I'm Jonathan Hill, and before I turn it over to Parthiv Shah to present an exciting case study showing practical applications of STAR-CCM Plus on Mars, I'd like to give you a brief intro to ATA engineering and STAR-CCM Plus. A few quick housekeeping notes. Everyone has been muted for now to avoid any background noise or distractions during the presentation. At the end, you'll be able to unmute yourself using the button in the bottom left corner to ask questions or share comments. And in addition, you can ask questions to the group or privately to me anytime using the chat, which is also accessible along the bottom menu bar, and we'll review those at the end as well. So most of you probably know ATA either through our role as a Siemens partner and reseller, or through our robust engineering services, and really these two go hand in hand. We have experience providing engineering services across a wide range of industries, and since we're solving the same issues as our software customers every day, it allows us to provide exemplary support. On the services side, our focus is on analysis and test-driven design. ATA is really proud to help our customers meet their toughest engineering challenges, whether that's performing ground vibration tests on state-of-the-art aircraft and helping to ensure the safety of theme park attractions, or analyzing next-generation spacecraft and planetary rovers. Of course, being experts with Siemens PLM software helps us do precisely that. Speaking of the software, this list shows the Siemens product lines that we use and can assist you with. Our technical support hotline service is staffed by experienced engineers who use these tools every day, and you can contact these subject matter experts either by phone or through our website. In addition, we can help with license sales, and we offer a variety of classes, with topics ranging from introductions to FEMAP and FEA to more advanced topics like dynamic response, super elements, optimization, and more. The full schedule of classes can be found on our website, and you can even request custom classes. Speaking of our software website, here it is. As we've discussed, it houses the full list of upcoming classes, and it can be used to contact our software support hotline. In addition, it has software product information and brochures, as well as links to download free trials. My favorite part has to be the growing collection of free resources. They're all developed by our engineers, and they're aimed at our customers' needs. These include white papers, training videos, tutorials, and APIs. And I'd invite you to check these out after the webinar wraps up. Now, before we get too much farther into the presentation today, I think it's helpful to frame STAR-CCM Plus inside the larger SimCenter portfolio. The SimCenter portfolio is a comprehensive suite of simulation software and test solutions, which includes FEMAP, NX, and NX Nastran, as well as many other products. Together, they can help your company address the engineering challenges of today's complex products. SimCenter combines simulation and physical testing with intelligent reporting and data analytics to produce digital twins that more accurately predict product performance and drive innovation throughout all stages of the product development cycle. Within SimCenter, STAR-CCM Plus is a powerful multi-physics simulation tool that uniquely integrates a wide range of physics with intelligent design exploration in a single end-to-end environment. This, combined with workflow automation and efficient parallel computing, enables engineers to conduct analysis and exploration of real-world problems, resulting in better design decisions earlier in the development process. The value of such a powerful solution is evident in this customer reference from Jaguar Land Rover in the UK. They do all their HVAC product development and testing using digital simulation without physical testing, which allows them to evaluate more designs earlier in the design process, leading to better design choices, reduced time to market, and significant cost savings. STAR-CCM Plus is able to achieve all this by delivering the following 6 key elements: realism with validated models that cover a broad range of disciplines in physics, productivity with repeatable and robust workflows, efficiency with high-performance computing capabilities and affordable licensing options, innovation with automated design and exploration and optimization, responsiveness with technology leadership and an aggressive development schedule, and success with dedicated customer support backed by a team of global experts. So looking through those 6 in a little more detail, let's begin with realism. STAR-CCM Plus is much more than an industry-leading CFD code. It's really a best-in-class simulation tool that provides a comprehensive set of physics models. All of these capabilities are accessed from a single integrated environment eliminating the need to learn and connect multiple tools. It offers both finite element and finite volume methods, allowing for the most appropriate numerical schemes for the physics being modeled. And STAR-CCM Plus can be coupled with third-party codes, giving you the flexibility to use the right tool for the job. STAR-CCM Plus helps cover your complete application scope in a single user interface by offering a broad range of validated models that simulate a variety of disciplines in physics, including those listed here. This slide is just a snapshot of the many industries and applications that STAR-CCM Plus can support. On the productivity front, STAR-CCM Plus enables every simulation model to be built using a repeatable and robust workflow, allowing models to be easily reused and updated to investigate a full range of design configurations and operating scenarios with minimal manual effort. Simulation models can even be templated, allowing best practices to be easily shared across your organization. STAR-CCM Plus is easy to learn and use, even for advanced configurations in physics, so there's no need to compromise between usability and functionality. It can be linked with CAD and PLM software so that geometry updates are automatically represented in the simulation, and it uses a single scripting language that allows you to completely automate your workflow, customize your experience, or set up a step-by-step process with simulation assistance. STAR-CCM Plus also delivers efficiency through high-performance computing to ensure that you can maximize the value of your hardware and fully leverage your investment in simulation. It has been developed with scalability in mind, offering solvers that scale to hundreds of thousands of cores and parallel meshing that reduces turnaround time by enabling mesh generation on clusters. STAR-CCM Plus also offers a range of affordable and customizable license options to meet your simulation needs and throughput requirements. STAR-CCM Plus allows for rapid innovation with built-in design exploration and optimization. Design Manager enables users to set up and automatically perform parameter studies within STAR-CCM Plus to evaluate families of designs, and users can take it one step further with the STAR Innovate add-on, which allows for single and multi-objective optimization studies that intelligently search the design space to identify the best designs using the trusted HEADS technology. On the right side of the screen, we have an example showing how Airbus has used STAR Innovate in the past to optimize the design of a mixer component in the environmental control system. They were able to evaluate over 250 designs in a much shorter time than would be required if the study was manually executed. And using that, they gained insight into the design sensitivity to changes in input parameters. To maintain a robust and efficient simulation process, STAR-CCM Plus has a long history of technology leadership, and it brings an aggressive development schedule, including 3 major releases each year that continuously deliver innovative technologies to respond to evolving simulation needs. Current users have the ability to influence the development of STAR-CCM Plus as well to meet immediate and anticipated simulation requirements. And finally, STAR-CCM Plus brings its users world-class customer support through the dedicated support engineer system. Your DSE will understand your needs as a customer and draw on subject matter experts inside Siemens PLM to provide the solutions to your challenges. In addition, a 24/7 customer portal provides access to knowledge base articles, a technical forum to exchange ideas and help other users, and downloads of new software versions as soon as they're released. As you can see, there's really a lot to be excited about with STAR-CCM Plus, but without too much more delay, I think I'll go ahead and hand it over to Parthiv for our future presentation.
Great, thank you, Jonathan. And thanks again to everyone for attending today's webinar. So can everyone hear me okay? Jonathan, am I coming out clearly on the audio?
Yep, you sound good to me.
Great. So I'll next talk about an application of STAR-CCM Plus. We'll talk about how ATA applied these advanced computational fluid dynamics methods in STAR-CCM Plus to support NASA Jet Propulsion Laboratory in the design of key sample collecting hardware for the upcoming Mars 2020 mission. So again, my name is Parthiv Shah. I am a senior technical advisor at ATA, and I'm the technical director of our fluid dynamics and propulsion discipline area. And today's presentation is about a project that we performed for our customer, JPL. I'd like to also acknowledge my colleague, Albert Robinson, who performed many of the CFD simulations and worked together with me on the project. So the next slide contains a short outline of today's presentation, and I'll start with a few introductory remarks, which include a high-level summary of what we accomplished. And then the bulk of the presentation will be about the Mars 2020 Fluid Mechanical Particle Barrier, or FMPB. And that's a key component designed to prevent the contamination of the samples that are going to be taken on the surface of Mars. So that presentation, or the presentation, will include a high-level overview of the mission, a discussion of the operational principles of the FMPB, and a discussion of how we used CFD in the design and the validation of the device. And finally, I'll wrap up with a summary. First of all, I'd like to state that everything that I'm presenting today is based on material in the public domain. So if people are interested in learning more about this very interesting application, this actual work was published in the journal Planetary and Space Science. Our customer was Dr. Yangos Michailidis, who is, I believe, going to join the web meeting today also. And he was kind enough to include myself and Mr. Robinson on the authorship of this paper as we did the CFD. A second thing I want to mention is a quick disclaimer on behalf of JPL themselves. This is a presentation from ATA Engineering on a project we've done, but this presentation doesn't actually constitute or imply any endorsement of any particular software tools or methods by the US government or by NASA JPL. Okay, so this is the executive summary slide, and this is really the main takeaways from my presentation. So the Mars 2020 mission involves landing a rover on Mars, and the unique objective of this mission is to be able to acquire, encapsulate, and cache samples of Martian materials for a possible future return mission to Earth. So that's really what's new about this mission. And it's for this reason that from a planetary protection point of view, samples must therefore be kept clean of any terrestrial organisms that may adhere, that is to say, hitch a ride on the rover or on other abiological particles. So a key feature to prevent this contamination is the device that I'm going to talk about in this presentation, which is the FMPB. And essentially, it's a carefully sized annular orifice that uses viscous resistance to limit the penetration of particles. And ATA used CFD simulations, specifically in STAR-CCM Plus, to demonstrate the principles of this solution under different environments that could be encountered at different parts of the mission, including Martian winds and dust devils. So the Mars 2020 mission is part of NASA's Mars exploration program. It has a number of science goals that you can read about in greater detail on this website that's listed here. But among the primary science goals is to characterize processes that formed and modify the geological record with the within the exploration area. Another key goal is to do astrobiologically relevant investigations on materials at the landing site and to assemble documented cached samples for a possible return to Earth. The rover itself leverages a lot of design and technology from the 2012 Curiosity rover. And as I said before, acquiring, encapsulating, and caching are what's new. And therefore, the astrobiologists have these stringent requirements to ensure that the samples don't get contaminated. And by contamination, we mean that terrestrial particles can carry some biological signatures on them, which, as I understand, they can actually survive the harsh environments of the journey, including going dormant and then possibly contaminating the actual sample itself. So on the next slide, I'll give a few more details on the Mars 2020 mission. So the launch window is going to occur over a few weeks in the summer of 2020, around late July to early August. And in general, these launch windows to Mars occur cyclically every 26 months or so. So after the launch vehicle separates, the rover, which is encased in an aeroshell, cruises to the red planet for over 7 months. And it's going to arrive somewhere around February of 2012. Just before it enters the Martian atmosphere, the cruise stage is going to separate from the entry, descent, and landing system, and that'll plunge uncontrolled through Mars's atmosphere, while the entry, descent, and landing system will go through a controlled activity sequence, which will lead to the rover's touchdown. The commissioning of the rover will include some critical deployments, some health checks, and also establishing communication with the Earth. And the prime mission of Mars 2020 is set to last about 1.5 Martian years. And you can see from the slide that 1.5 Martian years is about 3 Earth years or so. Because one Mars year is on the order of 2 Earth years, not quite. Okay, so now I'll talk about some of the key hardware related to the sample caching system, which is part of the rover. So this includes a robotic arm, the turret, and then the adaptive caching assembly, which is the hardware used to inspect, encapsulate, and drop samples onto the Martian surface. As you can see, it's a very complex assembly from this picture. It has a carousel for the various bits used to drill into the Martian soil, and it has assemblies responsible for storing, handling, and sealing the tubes. Additionally, there are various stations where the samples could be handled or analyzed. Within the sample tube storage assembly, which contains the empty sample tubes, is where we have the feature that the CFD simulations were performed on, the FMPB. So once the rover's landed, certain deployments occur. They introduce airflows to remove molecular contaminants from some outgassing hardware. And additionally, the doors of the bit carousel open, having been closed prior to this. So the sample tube storage contains the sterilized sample tubes and the seals, which are going to be protected by this FMPB glove, this fluid mechanical particle barrier glove. Okay, so this slide covers the operational principles of this glove, and they're somewhat straightforward. So there's a chance of particle penetration in the tube if there's a net inflow driven by a pressure difference or some sort of a Martian wind event. And so the FMPB glove separates the tubes from the external environment by a pair of thin orifice and cavity pairs that are arranged in series. And it's the narrow gap in these orifices that result in the fluid viscosity assisting to retard the addition of this mass into the system. So the key engineering requirement is to size this orifice to prevent any large particles from entering outright, and ensuring that any small particles penetrate no farther than a certain distance within the orifice itself. And so eventually these particles would then be able to fall under Martian gravity. As indicated here, gravity will be pointing down when the rover is on the surface of Mars. So NASA JPL, who managed the overall project, they took a multi-fidelity approach to substantiating that the design of the FMPB was sufficient. And that included first principles analytical modeling, having ATA perform 2D and 3D CFD simulations, which included Lagrangian particle tracking, laboratory water tunnel testing, and over the next slides, I'll describe these 3 efforts, which together help substantiate the FMPB design. Okay, so on the modeling front, the flow is essentially modeled as a network of orifice and cavity pairs, with each orifice having a resistance due to a locally fully developed flow. So it can be established from first principles that the flow rate will be in proportion to the driving pressure. and that the rate of change of pressure in each of the cavities will be proportional to the mass addition, which could then be related back to the driving pressure difference. And so in this way, the model becomes a pair of one-dimensional ordinary differential equations for the chamber pressure, and the coefficients are defined by the geometry and the atmospheric reference pressure. And so these systems were solved using a numerical integration tool. So that was the analytical model. The model for the flow then establishes what the trajectory of the particles of these biological particles could be by essentially solving F equals ma. And with dimensional analysis, it was found that the forces become a balance between the drag forces due to the pressurization or the wind acting on these particles and the Martian gravity. So this is where ATA's role came in terms of performing CFD in order to substantiate these analytical models for JPL, or to help substantiate them. So we use STAR-CCM+, and we perform time-accurate, low Mach number CFD simulations using an ideal gas assumption to simulate the Martian atmosphere. And here in the picture, you see an example of some of the computational domains. We did both 2D and 3D time-accurate simulations, and they included the fluid mechanical particle barrier and the sample tube cavity flow path, as well as some of the external fluid around that device. We took advantage of STAR-CCM's unstructured hexahedral trim meshing generator, which would allow us to get adequate resolution in the critical areas, such as orifices, while also making the simulations very computationally efficient. And in addition to simulating the flow itself, STAR-CCM+ allows you to simulate the particle dynamics through a Lagrangian framework, and that was used to quantify the particle's penetration. So this slide here just shows some early results, which were used to show that the CFD results match the analytical model well. So on the left, we show that there was good agreement with the cavity pressurization time history, and on the right, we found that there was also good agreement for the penetration of 0.3 micron particles over a range of external wind speeds. And so this certainly gave us confidence that the model itself that was assumed for this system was appropriate. Now, as I mentioned, STAR-CCM+ has the ability to simulate Lagrangian particles. This slide shows an example of that capability under the influence of Martian gravity. So you'll see this animation that's looping. So in general, these simulations were performed for both a sudden pressurization and also a direct flow type of an event that may occur from a Martian wind. And in these simulations, groups of particles were made to appear periodically in time very close to the opening of the orifice. And so the animation I'm showing you is a direct flow simulation with a Martian wind of about 15 meters per second, which would represent one of the worst expected winds based on known data. So you can see that the particles are being carried through the first orifice, but then they're getting arrested very near the cavity entrance, and eventually they will fall back due to their own gravity, which is downward in this visualization. You also can see that some of the particles end up recirculating just to the side of the body, which is interesting, but it's not directly a concern from the point of view of the performance objectives of the FMPB. So here we're doing a fluid dynamic simulation, and then because these particles are small, they're not directly coupled with the fluid dynamics, but they respond to the flow itself in a one-way sense. But STAR-CCM+ has the ability to run both one-way and two-way coupling with Lagrangian particles. Okay, so finally, the CFD and the modeling were also supplemented by some flow visualization that was performed at the Caltech water tunnel. And the goal here was to investigate the role of asymmetries in terms of whether they could lead to noticeable penetration. So in general, the water tunnel can match the Reynolds number, but it cannot match the Stokes number. which is the ratio of the response times of the particles on Mars and the fluid. And so for this reason, the particles were not actually used in the water tunnel, but the penetration of the dye itself was used as a surrogate for particle penetration. And so from these series of pictures, we find that at 0 degrees angle of attack, there was no dye penetration into the cavity. However, at a finite angle of attack, for in this case 30 degrees, there was evidence of some dye penetration. However, the analysts could look at the timescales from the film and could infer that this penetration would only really occur for Martian wind speeds that were much, much higher than the worst case scenario expected on Mars. So this was another key aspect of risk reduction in this work. Okay, so we built these models. There's a 1D analytical model. There's high fidelity CFD simulations to substantiate the model. There's some wind tunnel testing, and the simulations were done under a set of assumed boundary conditions. And so the next two slides discuss work that was done to determine whether the assumed flow boundary conditions themselves were reasonable. So first, it was determined that the first non-negligible flows on the FMPB might occur during entry, descent, and landing. However, from the entry interface through the heat shield separation, the pressurization that could occur was found to result in fairly low local flow speeds, lower than what was simulated with the worst case CFD. So it was determined that the FMPB would meet its design requirements in this condition. So on the next slide, finally, during the rover surface operations, the adaptive caching assembly has its belly pan dropped, and there is the possibility of the exposure to the Martian winds. I mentioned those before in the CFD simulations. So the question here is, could the Martian winds be large enough to theoretically create an adverse penetration event? So the way that this was addressed was using a defeatured model of the rover cavity. So on the left, we have data, a statistical distribution of the Martian winds was taken from the 1976 Viking Lander 2. And that would help establish what the worst case scenarios were. And then a simulation was performed assuming an atmospheric boundary layer over a highly defeatured version of the rover, which is essentially a box with an exposed cavity underneath, which is simulating the adaptive caching assembly with the belly pan open. And in this case, large eddy simulations were used to estimate what the local velocities would be. So this animation shows how we began with a steady Reynolds average Navier-Stokes flow field simulation, and then ran a large eddy simulation with the goal of probing the region of the cavity that's shown on this in this open area to see what kind of flow velocities would occur based on the worst case known Martian winds from the Viking Lander data. And based on this, the 1D model then could then be used by running the different statistical scenarios. So that kind of brings us to the end of the presentation. And basically, the overall conclusions relate to how the fluid mechanical particle barrier was substantiated, how its operational principles were substantiated in order to convince the designers, especially the astrobiologists, that in fact it would serve its purpose. So to summarize, the Mars 2020 mission leverages proven technology from the Mars Science Lander Curiosity mission, though the caching of samples creates a new and unique requirement from the standpoint of planetary protection. CFD and STAR-CCM Plus was used to establish the operational principles of the FMPB, as well as to verify a first principles analytical model. And this demonstrated that even in the 99th percentile nominal Martian wind, the penetration could be limited to a relatively short distance within the first FMPB orifice. Okay, so that brings me to the end of my presentation, and I can open it up to any questions that people might have. And we also may have Dr. Michaelides of Jet Propulsion Lab on the webinar. So if you have any additional questions about the mission that I can't answer, he may chime in as well. I thank you all for your attention, and we can open it up. Thank you.
So it sounds like we probably won't have any questions today, at least not at the moment. If you have any in the future, definitely reach out to us. We'd love to hear from you. As well as if you have any topics you would like to see us cover in future webinars or future resources for the website. Again, thank you, Parthiv. That was really great. And I hope everyone has a great day. Thanks.